Okay, good evening, guys. I'm going to give you more examples on compression members. And before I start this, I will explain more how to determine the buckling length because that's a crucial step in the design of compression members. Okay, let us have an example here. For example, we are having a truss like this. This is part of a truss, and here we are having subdivided system. These are the roof purlins, and we are having here struts connected to the truss at the bottom chord. The shape of the upper bracing will be like this. So this is the upper wind bracing, and here the lower wind bracing for some reason looks like that. If this height is h and the typical distance here is a, now it is required to determine the buckling length of members 1, 2, 3, and member 4, 5, and 6, member 7, member 8, and member 9. So I'm going to draw here a table. This is the member, and LX, which is the in-plane buckling, and LY, the out-of-plane buckling. And here we are having members 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay? As we said before, the in-plane of the truss, this is the X-plane. From there, we determine the magnitude of Lx, which is the buckling length about the x-axis. Now, let us start with member 1. Where is member 1? Member 1 is here. The boundary conditions of this member, it is hinged. So if it wants to buckle in the x-plane, it will buckle like half sine wave, like pinned column. Therefore, the buckling length, which is the distance between the two inflection points or the zero moment points, will be equal to this horizontal distance, which is A over 2. Type. In order to see this member in the out of plane, I will have to look to the truss from the top. So here we have this member. Okay? If you are looking from the top, this will be the out of plane, the movement of the member in the out of plane. In the out of plane, if you look to this member, it is connected to a purlin here and a member in the diagonal, and also it is connected to another purlin there. يبقى if this member 1 wants to buckle, it will buckle this way as well. It means that the distance between the two inflection points when it buckles in the out of plane, Ly, will be the distance A over 2 as well. يبقى this is the Y plane from which we are getting Ly, which is the out of plane buckling. طيب, how about member 2? Member 2 in the in plane, it is hinged. All of the members in the in plane, they are all hinged. يبقى therefore the in plane buckling length will be directly the geometric length of the member that appears in the X plane or in the elevation of the truss. يبقى for member 2, it goes without saying that this in plane buckling length A will be also equal to A. How about in the out of plane? In order to see how this member will behave in the out of plane, I will have to look to the top view. When you look to the top view, you will see the upper bracing. يبقى the member is here. Okay? Now we are having a strut or a purlin here, and we are having a purlin here. يبقى this member, when it buckles, it will buckle like that. Again, the two inflection points are the two ends of the member. يبقى therefore it will be A. طيب, how about member 3? Don't ask me about the in-plane buckling length. It goes without saying that it will be equal to directly, it will be equal to A. But how about the out of plane? In order to look to this member in the out of plane, I will have to look to the truss from below. So I'm going to look to the lower bracing. Where is member 3? Member 3 is here. يبقى this point is braced and this point is braced, يبقى therefore this should be the buckling length. But the Egyptian code is telling us that if these 2 points are not braced in the out of plane, like what is happening here, this point is braced in the out of plane, but this one is not. It is not connected to any member in the lower bracing. يبقى you should take 0.75 of the distance between the braced points. This point is braced and this point is braced, so you have to take 0.75 of that distance, which is 0.75 times 2A, which is basically 1.5 of A. Okay? طيب, يبقى we finished then the top chord and the bottom chord. How about the diagonals? Let us take member 4. Member 4 is this member. In the in plane, it will buckle between this point and this point this way. Always it will be the geometric length. So for member 4, this will be root A square plus H square, which is the length of the member. طيب, in the out of plane, unfortunately, there is no specific view. I can look to this member and see how it looked like in the out of plane. I will have to investigate the upper end of the member, which is this point. It is braced by the effect of the purlin. And this point is braced by the effect of the strut. يبقى this point is braced in the out of plane, and this one is also braced in the out of plane. So the buckling length in the out of plane will be also the length, which is root A square plus H square. How about member 5? This member. Now I'm having in the in plane, it will buckle this way. Because don't forget that this is a joint. يبقى the length here will be root A square plus H square over 2. But in the out of plane, this point is braced and this point is braced and this point is unbraced. يبقى the two ends of the member is not braced in the out of plane. So I will take 1.2 of this length. Okay? Again, now this point is braced by the effect of the strut, and this point is braced by the effect of the purlin. But this is not the end of member 5. Member 5 is here. This point, we are talking about this point. This point is braced due to the effect of the lower bracing, And this point has nothing to hold it because I'm having a strut in this level and a strut and a truss in this level, and we don't have anything, of course, in the middle. At this point is unbraced. If you look to our notes, you will see that for the diagonal members and for the vertical members, if one end of the member is braced in the out of plane and the other end is not braced, then we take 1.2 of its length. We have to take here 1.2 of its length, which is root a square plus h square over 2. Okay? Type member 7. Member 7, again, in plane buckling length will be the length h. This is member 5. Member 6, I'm sorry. Let us see member 6. Member 6 is that member. Okay, again, in the in plane, it will be this length, and in the out of plane, it is braced at this point and also unbraced at this point. I will take 1.2 of that length. It will be identical to member 5 exactly. The in plane buckling length will be root a square plus h square over 2, and for the out of plane, this point is braced and this point is unbraced, so I will take 0.6 of that, or 1.2 of the length root a square plus h square over 2. Okay? Type for member 7, the buckling length in the in plane is the height h, and in the out of plane, this point is braced because of the effect of the purlin, and this point is braced because of the effect of the strut. Again, I will take h in the out of plane. Type member 8. The in plane buckling length is always equal to the geometric length of the member. And in the out of plane, this point is braced by the effect of the purlin, and this point there is nothing to hold at this point, right? So according to the Egyptian code, I will take 1.2 of that length. As long as you are having one end is braced and the other is unbraced, you take 1.2 of the length. Exactly like member 6. Member 6, this end is braced and this end is unbraced because I have no struts that is holding the member in the out of plane, then it will be 1.2 of that length. Here it is 1.2 of h. How about member 9? The same thing, this member. In the in plane, it will have to buckle at a distance of h over 2, which is the geometric length of the member. And in the out of plane, this point is braced by the effect of the purlin, and this point is not braced. We take 1.2 multiplied by h over 2. Okay? Now, as long as we understand this, you will not have anything more difficult than that. It is clear that for the top chord members we are taking, or all of the members, we are taking the geometric length for the in-plane buckling. For the out-of-plane buckling, if the member is a top chord member or a bottom chord and is braced from the 2 points in the out-of-plane, we take its length. But if, for example, like member 3, this point is braced and this is not braced, we search for the other bracing point and we are going to take 0.75 of that length. For the diagonals and the verticals, if one end is braced and the other end is not braced, we take 1.2 of that length, either in the vertical or in the diagonal. Okay? So this is to explain or to review the buckling length for truss members. Now let me solve with you 2 more problems on compression members. Going to solve a problem. Imagine that we are having a truss like this. This truss actually is supporting a cantilever, or is a cantilever supporting a shed outside a frame. So here we are having the frame, and attached to the column we are having this truss. The height of the truss here is 1 meter, here it is 2.2 meters, and the distance here is 2 by 3, which is 6 meters. The upper bracing, we are having a purlin here and a purlin here and a purlin here at each joint. So the upper bracing will be something like that. So all of these points are braced in the out of plane. The lower bracing, I don't have except a strut at this point, which is this strut. And we are having a strut at the position of the column. And all of these, this point and this point, they are not braced in the out of plane. It is required to design member 1 if the design force, now we did the load combination table and we got that this member is subjected to compression, -6, and also in another load case, it is subjected to +8 ton. The connections are bolted and the bolt diameter is 20 millimeter. Now it is required to design member number 1. What will be the steps? First of all, we will determine the buckling length. In the in plane, as usual, it is the geometric length. So we are having this distance here is 0.4 from similarity. This is 1.4 and this is 2 meter. We can get the length of the hypotenuse. So the length of the hypotenuse here will be 1.4 square plus 2 square. And if you did this, you will get the value of 2.44 meters. This is Lx. For Ly, this point is braced in the out of plane because of the effect of the purlin, and this point is here. There is nothing holding this point from movement in the out of plane because we are only having a strut at this position and a strut at this position. Therefore, the length in the out of plane will be 1.2 times 2.44, and if you did this, you will get 2.93 meters. Now, the type of cross section. The design force that we have, either tension or compression, it is less than 8 tons in magnitude. And the buckling length, the largest buckling length is 2.93, which is less than 3 meter. Therefore, I will use one angle. The value of I, or the minimum radius of gyration for the angle, is 0.2a. For the stiffness condition, we are having L maximum over I minimum should not exceed 180. Take care that for the angle, this is the section, we have the axis that is giving the minimum radius of gyration is this inclined axis. But unfortunately, we determined the buckling about the X and the buckling about the Y. So we are doing an approximation. We are taking the maximum buckling length, which is obtained to be 2.93, divided by the minimum radius of gyration, which is 0.2a. Therefore, 293 over 0.2a, that is equal to 180. From there, a should be bigger or equal to, if you did this, you will get 8.13 centimeter. And this is the first requirement. Of course, the member, as long as the member is subjected to compression, regardless to the ratio between the tension and the compression, you will have to substitute the limit of the stiffness condition to be 180 because it will supersede or will govern the limit of the tension member. This is our first condition, that the angle leg should not be less than 8.13 centimeter. طيب. For the other step, we are having the construction condition. We are having A minus T should not be less than 3 times the bolt diameter, which is 6 centimeter. This will be the second condition. After that, the condition of the area. Now, we need to start as either designing compression or tension and then check for the other force. Here, since the tension design force is less than 2 times the compression, if you multiplied the compression by 2, you will get 12. Then the tension is less than twice the compression. I will have to start as compression. In order to start as compression, we know that I'm going to use the design force, which is 6 tons. If you look to your notes, if the design force is ranging from 5 to 10, then we can assume the magnitude of F critical to be 1.2 ton per centimeter square. Assume F critical 1.2 ton per centimeter square. Therefore, the area of one angle will be the design force, which is 6, divided by the value of phi is 0.8, and the average or the assumed critical stress is 1.2. And take care, the section is unsymmetric because it is composed of one angle. Then we are going to reduce the stresses by 0.6. 0.8 is the strength reduction factor for compression members, 1.2 is the assumed F critical, and 0.6 is a factor to account for unsymmetry. Then the area of the angle will be 10.42. And this will be the third condition. So I'm having 3 conditions here. The first condition is that the angle leg should not be less than 8.13. The difference between the angle leg and the thickness should not be less than 6 centimeter. And the third condition, the area of one angle should not be less than 10.42. Therefore, we are going to use one angle 90 by 9. The value of A is 9 centimeter. The value of A minus T is 8.1 centimeter. And area gross is 15.5 centimeter square. If you check here, this is our selection. Okay? We are having A is satisfying the stiffness condition. A minus T, which is 90 millimeter minus 9 millimeter, gives 81 millimeter, يعني 8.1 centimeter. It is satisfying the 6. And area gross is 15.5, and what you need is 10.4. Now we have to take this angle and check for whether it will be safe or not. Let me erase this, please. Okay, check on strength. What will be the steps? I will get L maximum over I minimum. The maximum buckling length is 293. centimeter. I minimum, we selected an angle 90 by 9. So I minimum is 0.2a, which is 0.2 multiplied by 9. If you did this, you will get 162.77. Therefore, we get lambda c, which is L over I over pi square root of F yield over E. Now, if you did that, you will find that this is 1.75. 1.75, it is more than 1.1, therefore we are having elastic buckling. Therefore, F critical will be 0.648 over lambda c square multiplied by F yield, which is 2.4. If you substitute in the equation, the value of lambda c is 1.75 and F yield is 2.4, we get here the critical stress, and it will be 0.507 ton per centimeter square. Therefore, we get the capacity of the angle phi P nominal. The value of phi is 0.8 and the area of the angle is 15.5, that's from the table. And the stress is 0.507, that's the one that we calculated accurately now. But take care that this angle is unsymmetric. I will have to multiply this by 0.6. So if you did this product, you will get a value of 3.77. Is this okay or not okay? Now we know that the design force he gave me in the question, it is -6 or +8, right? Now we were designing on the compression. The capacity of the angle, it can afford 3.77 and it is subjected to a force of 6. This is less than P ultimate. This is not good. It is not safe. What can we do? Now, you don't check for the angle for the other thickness, which is 11 millimeter, but you will have to go for the other family. The other family is 100 by 100 by 10, or the family that follows, which is 110 by 110 by 10. So you don't increase the thickness of the angle, but you increase the angle leg as well. So the systematic steps that you should follow, you should change your selection. Now this selection is not suitable, so you will have to take one angle 100 by 10 and repeat the same process. If you repeated the same process, you will still find that it is unsafe. You will end up using one angle 110 by 10. Let me show you that. Use one angle 100 by 10. It will be unsafe as well. So, and then I'm going to do another iteration. I'm going to use this angle, which is one angle 110 by 110 by 10. The value of area gross of this angle is 21.2. So let us check this angle as final check. So the first iteration, we used one angle 90, it was unsafe. The second iteration, we used one angle 100, unsafe. And then the third iteration is this one. So I will take L maximum over I minimum. L maximum is 293 over I minimum. This is one angle, so it will be 0.2 of the angle leg here is 11 centimeter. So if you did this, you will get 133.2. Therefore, lambda C will be L over I 133.2 over pi square root of F yield, which is 2.4 over the Young's modulus 2100. We get here the value and it will be 1.43. This is again bigger than 1.1. We are still having elastic buckling. As long as we are bigger, lambda C is bigger than 1.1, therefore F critical will be 0.648 over lambda C square, which is 1.43 whole square, times F yield, which is 2.4. We get this value and it will be 0.76. Therefore, phi Pn, the resistance of the member, will be 0.8 times the area, which is 21.2, times F critical 0.76. And don't forget that this is one angle unsymmetric member. You have to multiply by 0.6. So the result, if you did this, it will be 7.7. Now it is bigger than 6 tons, therefore it will be safe. Okay? Now, he told us that this is a tension compression member, but we have to check for the tension. We have reached this angle. We are going to check whether this angle is satisfactory with respect to tension or not. We are not going to do any more iterations, but this is our final design and we are going to use it in our check. Okay, so we are going to check as tension. Okay, we are having angle 110 by 110 by 10. The area gross is 21.2 centimeters square. First, I will go for the gross section yielding. Phi Pn equals, the strength reduction factor for the gross section yielding is 0.85. The area of the angle is 21.2 and we multiply by F yield, which is 2.4. When you calculate this number, it will be a huge number, 43.25 tons, which is bigger than 8 tons. Take care. Now I am comparing to the tension, because this was tension compression member, so I am comparing now to the tension force. So this is safe. For the net section fracture, we know that this member is bolted. We don't assume the net area to be 0.85 of the gross, because already we are having the bolt diameter. We have all the knowledge about the angle, so we can get area net will be area gross minus the diameter of the hole times the thickness of the angle. So this is 21.2 minus the diameter of the bolt is 2 centimeter and the hole must be wider by 2 millimeters, so this is 2.2 times the thickness of the angle, which is 1 centimeter. So if you did that, this will be 19 centimeter square. Therefore phi P nominal, the strength reduction factor is 0.7, the net area is 19, and the F ultimate is 3.6. And don't forget, we have to multiply by the shear lag factor U. In this case, it is 0.75 because connections are bolted. So if you did this, you will get a value of 36. Again, this is bigger than 8 tons. يبقى therefore it is okay. يبقى this will be the steps that we are following to design member 1. One last thing, maybe will not take more than 10 minutes. If we want to check the design of member 2, member 2 will be given to us, okay? And we need to check the design of that member. So this is another example. Example number 2. Check safety of member number 2 if it is composed, if P ultimate applied to that member is negative 20 tons and it is composed of two angles 90 by 90 by 9, the area gross of which is 15.5 centimeter square, and the connections are welded. Solution. So in this question, he is telling us if this member 2, is composed of two angles back to back, 90 by 90 by 9. You are no longer selecting. You have to start with the given information to you. And this member is supporting a 20-ton force compression that is coming from the load combination equation. And the member is welded. We don't have bolts here. We have to satisfy the stiffness condition and the strength condition. To do that, I will have to get first the buckling length. For the in-plane buckling, this member, again, if it wants to buckle, it will buckle like this in the in-plane. Each joint is considered to be a pinned support. Therefore, the buckling length is 2 meters in the in-plane. In the out-of-plane, this member is here. It is only braced at this point and this point, it should buckle this way. But the Egyptian code told us you have to take 75% of that length. Therefore, we take 0.75 multiplied by 6, then it is 4.5 meters. Now for the stiffness condition, take care. Now, for this member, it is composed of two angles back to back 90 by 9. Okay? We got the buckling about the X and the buckling about the Y. We have to, when we check the stiffness condition, we have to divide Lx by Ix and Ly by Iy. We have here Lx over Ix equals 200 divided by the angle leg is 9 centimeter, and we know that Ix here is 0.3a and Iy is 0.45a. So this will be 0.3 times 9, and Ly over Iy will be 450 over 0.45 times 9. Okay? So if you did this calculation, you will get here, this is 74 less than 180, and this is 111 also less than 180. We are checking now, we are not selecting the angle. So we know we got from the figure the value of Lx and Ly. We divided Lx by the minimum radius of gyration about the X and Ly about the radius of gyration about the Y. which is here 0.3 of the angle leg, which is 9 centimeter. We got 74, and this is already satisfying the stiffness condition. And in the other direction, 0.45 of the angle leg, which is 9, we got 111, which is less than 180. Now, we want to see whether the angle can afford or can stand the force of 20 tons. Therefore, we have to calculate F critical. Which slenderness ratio are we going to use? The largest, because the largest will give us the least value of lambda, and corresponding to that will have the least F critical. Always we are taking the largest L over I. So the last step, we have to check on strength. L over I, the maximum value was obtained 111. يبقى lambda C will be L over I over pi square root of F yield over E. And if we calculated this, we will get 1.2, which is again bigger than 1.1. If it is less than 1.1, it would have been inelastic buckling governing, but here we are having elastic buckling. يبقى F critical be 0.648 over lambda C, which is 1.2 square, times F yield, which is 2.4. We get this value to be 1.08 ton per centimeter square. Therefore, phi P nominal will be, the strength reduction factor is 0.8. We are having two angles back to back, so the area will be 2 times the area of one angle, which is 15.5, times F critical, which is 1.08. The section here is symmetric, so we don't have the factor 0.6. If you did this, you will get 26.8. And this is more than 20, يبقى therefore it is safe. We found that the angle can support up till 26.8 tons, and the applied design force is 20, يبقى therefore the angle is correct. يبقى in general, the problems that we can get, either that we are designing a problem from the very beginning, we are selecting the angle, or we are given the angle profile and you are checking whether it is satisfactory or not. Okay, now you should be able to solve the assignment problems on the compression members and the tension compression members. And the last part remaining in our course will be the explanation of the detailing. And this I'm going to explain in 1 or 2 lectures for you. And then after that we can have revision if you would like to, and discussion sessions. Thank you.